All right, welcome back to Mr. P. Helps with Algebra 2. This is Unit 2, Topic 3, SLT22, which is rational functions, but when the denominators have a degree of 2. So we're graphing them and finding out the key features of them and all kinds of stuff. So what I mean by that is we've been doing 1 over x as the parent function, but now we're going to do 1 over x squared. So with a degree of 2 on the bottom. All right, so when you look at this, this has a degree of 1. This is the same thing as we've been doing. So notice where the new origin is at. So it looks like it's a transformation to move right 3 and up 2. So that equation would be right 3 up 2. And then this point right here, it's a little bit hard to tell. So the next one is going to be up. Looks like it's just positive 1. And then this one over here, so the transformation moved left 2. So that's left 2, and it's up nothing. So then all I have to do is ask myself the next point is 1 down, just like that. And I'm done. So label the asymptotes. So I probably should have done that first, but this asymptote right here is at x equals 3. This is y equals 2. Remember that 2 goes from right there. That 3 goes from right there. This is y equals 0, and x equals negative 2. All right, distance. So when you talk about like a spray paint can spraying on a wall, so if you hold the spray paint really close, let's say it's only like 1 inch away from the wall, so it's only going to spray very intensely on this one little tiny square. But if you hold it 2 inches away, it's going to make a bigger circular. I know when you spray blue spray paint, it's going to make a circular, but let's assume for right now that it's making a square shape. It's gonna hit a bigger part of the wall, but since you're holding it further away, but it's not going to be as intense, meaning, you know, this is really dark blue, but this is not as blue. And if you hold it 3 inches away, then it's going to make a bigger, it's going to cover a bigger area, but it's still, once again, it's going to become less and less intense. So that's kind of the same thing that's happening here. So when you have like a shining of light, so this is the intensity of light, follows inverse square law. So it says basically, and this is one of the things that uses a degree of 2 on the denominator. If you are 1 meter away from the light source, and this is the equation right here, so I'll let you read that yourself. What is the intensity of the light? Well, if you have 1200 and you divide it by a distance of 1 squared, so that's your intensity. Your intensity is equal to 1200 divided by 1 is 1200. So your intensity per distance is equal to 1200. Now, I don't know exactly what that is, 1200 watts. It may be in lumens or whatever else you're measuring the intensity of light in. If you are 5 meters away from the light source, what is your intensity of light source? Okay, so you might be thinking, well, hey, I can just divide that by 5 because it's going to be 1/5 the brightness. Well, no, it's not, actually. That's not the way that light works. So it's 1200 divided by 5 squared. So you're actually dividing it by 25. And 25 goes into 1200, let's see, 48 times. So that's the intensity. So notice that the intensity is much less. It's not 1/5 of this. It's actually 1/25 of that. So the further you hold something away, it's actually going to get much less intense. Skipping that, and sketch the graph. So we did a couple of these. So divided by 1200 divided by 25, I need to pull out my... Alright, so now that I got my calculator, I'm going to do 1200 and divide that by 5 squared, which is 25, and that gives me 48, like we had done before. And I'll just keep doing the same thing. So I'm going to now divide 1200 divided by 100, and that gives me 12. If I divide 1200 divided by 225, which gives me 5.3 repeated, and if I do 1200 divided by 400, let's try that again. 1200 divided by 400 gives me 3 exactly, and 1200 divided by 25 squared, which 25 squared is, I lost track of that. So 25 times 25 is 625, sorry, and 1200 divided by 625 is 1.92. Alright, so in the context, we'll get to that question in a second. So 5 was 48. The next thing I want to do is graph it. 10 was 12. Now you're probably going to notice right away that it looks very similar to what we have been doing with rational functions before, and there is a reason for that, which I'll show you in a second. 25 is 1.9. Yes, it does look exactly the same as all the other rational functions, but it's not going to look the same when you compare the entire parent function, which is 1 over x squared. And I'll show you that in the next one. This is the context of this is we use negative values for D. Now, the reason why you can't use the negative values for distance is because you can never have negative distance away from the wall. So when you're using a spray can or a light or whatever it might have been about, yeah, this was the flashlight, sorry. You can never hold the flashlight negative 1 feet away from your face. This is not possible. So even if you're holding it 1 foot behind you, it's still 1 foot behind you, so therefore it's still positive 1 foot away. Distance can never be negative. What happens to the intensity as the distance increases? So the further the distance increases, the intensity decreases very, very, very rapidly, especially in the beginning. So it gets much, 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 much less bright in the beginning, and then less and less, it decreases less and less as you go on. So now I told you before that the graph of a 1 over x squared is not going to look the same. So this is 1 over x that we've been dealing with. That's our parent function. That's an odd function, as I mentioned in prior videos. And the reason I know is because all points on this part of the graph are always opposites, or they're a perfect reflection over the origin. So this point's a perfect reflection over this origin. Same with this point over this part on the origin, sorry. And the difference here is you're going to notice that it's not going to be opposite sides. This time it's going to be a perfect reflection over the y-axis, which makes it an even function. Anything that's a perfect reflection over the y-axis doesn't have to be a rational function. It can be any kind of function. But anytime it's a perfect reflection on both sides, then you call it an even function. So you draw the asymptotes where you think they would be, and I think I already drew on that one. They have the exact same asymptotes. So that's one thing that you should notice, is that both of these functions, both when they have a degree of 1 or 2, they both have the same asymptotes, same transformations involved. The domain here would be all real numbers, set of all real numbers in which the domain cannot be 0. The range can be all real numbers as well, in which the heights cannot be 0. It's going to be the exact same thing for over here, except the range is going to be y is greater than 0. So that's the only thing that's changed here. So here the height can be anything except for 0. Here the height can only be things that are above 0. It never has a height down here at the bottom half. But the domain's going to stay the same. Domain's going to be all real numbers in which the domain cannot be 0. Horizontal asymptotes are going to be the exact same as both of these and the vertical asymptotes. The horizontal asymptotes is going to be y equals 0, and they both have x equals 0 as the vertical asymptotes. End behavior. They both have the same end behavior as well. This graph, the further you go left, so as x is going to the left, the height is getting closer and closer and closer to 0. As you're going further to the right, the height is also getting closer and closer and closer to 0. So it's going to be the exact same thing over here. So the further I go to the left, it gets closer to 0, and the further I go to the right, it also gets closer to 0. So the same thing I wrote here, I would also write here. So circle all the applied. They have the same vertical asymptotes, horizontal asymptotes. They have the same domain. They do not have the same range, but they do have the same end behavior. So what makes them different is this is an this is an odd function, this is an even function, that's one main difference. And they do not have the exact same ranges because it's using two different quadrants of the graph. That's the difference. Similarities, they have a lot of similarities. Same asymptotes, same domain, same end behaviors. So there's a lot that they have in common. Alright, so now let's take a look at one that has a degree of 2. So this is the equation, so it's still dilation on top. This is the left and right transformation. This is the up or down transformation. So that's always going to look the same pretty much for all functions. This transformation is 2 to the right, and that's it. So the asymptotes here are x equals 2 and y equals 0. Domain is all real numbers except for 2, and the range would be everything above 0. So x can be all real numbers except x cannot be 2. Transformation, like I said before, was just right 2. That only has one transformation. That is it. This has two transformations. So this has been shifted down 3, but it also has a reflection over the x-axis. So these graphs, if you look at this graph, it's been flipped to the bottom side. So what you know is the next point is 1 down, so you know that the dilation factor is going to be -1, so is the equation. The asymptotes, so that's x equals 0 and y equals -3. Domain can be anything except for 0. And the height can be anything below 0. So no, not 0, sorry. It's going to be anything below -3. So it never has a height of -2 or anything above that dotted line. It can never be that dotted line either. And it looks like that was it. Thanks again for watching. Please give it a like to help you learn something about how to graph functions, rational functions, with a degree of 2 as the denominator. All right. Talk to you later. Have a good day.